Okay, so to start, what really is our second semester topics, even though this may be introduced in the first semester, just going to have a quick video that talks about something that we are going to introduce and spend a lot of time, probably about 2/3 of the semester focusing on, and that's something called an integral. And as you've seen, I kind of created a table right here where on one side on the left I have properties of a derivative, on one side to the right I have properties of an integral, and you'll see that they have a lot of things that are kind of similar between them. It turns out they are actually related and dependent upon one another, but we will learn about that, a little bit future in other units. We're going to kind of reduce integrals down to something fairly simple in this unit and then kind of add pieces of information as we uncover more. But to begin, let's just look at how we write derivatives and integrals. Realize with the derivative we had f prime of x, dy dx, all that kind of stuff. With integrals, we have this weird shape. The integral shape is actually this thing that looks kind of like an S. Okay, we put a function inside it. This means take the integral with respect to, just as when we had dy over dx, that meant take derivative with respect to. Okay, so it's kind of just another respect rule in there. But this whole symbol basically means take the integral of the function f of x, whereas this symbol meant take the derivative of f of x. This meant take the derivative of y with respect to x. So that's kind of the symbols that we use to define an integral. Now let's look at the representations. Let's go back to derivatives. Remember all last semester, if you remember anything from last semester, I hope that you'll remember these two things that I just starred. That a derivative represents graphically the slope of a line tangent to the curve. More conceptually, it represents an instantaneous rate of change. Now look at these two representations of the integral. An integral represents graphically an area under the curve. We'll talk about what that means in the next slide. Or it represents a net change. So as you see, there are two relationships for what integrals and derivatives represent. They have both a graphical understanding to them and a conceptual understanding to them. And it's important that you understand both. Okay? Now also remember about derivatives that a derivative can either give you a function or a value. If we, for instance, evaluate f prime of x, that's giving us a function. And what that function can be used for is to determine these two things that we talked about right here. It's a function that can either give us the slope of the line tangent to the curve at any point, or a function that can tell us what the instantaneous rate of change of some quantity is at any point. Okay? Now look at an integral. Okay? An integral is a function which can give these two representations above. If we evaluate this integral, it's a function that can help us determine the area under a curve or determine the net change in some quantity over some interval. One thing you might notice is a difference between a derivative and an integral is that a derivative is based on something occurring at one specific point. If we come down here, if we look at f prime of a, that is no longer a function. That is a value like 5 or 10 or 2.131. Okay? It's a value. It is a number. And what that value represents is that is the specific value for the slope of a line tangent to a curve at the specific point of A. Okay? It also represents a number for the instantaneous rate of change, again, at that specific point A. So you notice derivatives are concerned with something occurring over a specific point. Integrals are a little bit different. They're concerned with something occurring over an interval. So what we use is this symbol right here. The integral, this is called the lower limit of integration, or A. This is called the upper limit of integration, or B. So if we take the integral and we add that A and B to that integral symbol, that will give us a specific value which represents the area under the curve over the interval A to B, or it represents the net change in a quantity over the interval A to B. So integrals occur over intervals, whereas derivatives occur at one instance. But again, they're actually related to each other and they're dependent upon one another, but we will get back to that in a little bit. What's important that you understand right now is that if you see this symbology in the future, you just understand, oh, that means area under the curve, or it means something for net change. We'll get into the net change in another unit, but this unit, we're really going to be focusing on this first definition of an integral as an area under a curve. All right, so let's talk about that a little bit more. So if we go to the next slide here, this is what we mean by area under the curve, okay? So it's also called a definite integral. If I have limits of integration, this a and this b here, that's called a definite integral. If I have something like this, that's called an indefinite integral. Again, we will talk more about indefinite integrals as we go on to next units, but we're going to be focusing more on definite integrals for this first unit right here. So what all this symbol means is when we say take the integral from x equals a to x equals b of f of x, what we're saying is, one way we can think about this is we're saying, tell me the area under the f of x curve from x equals a to x equals b. So if we go to this drawing that I have down here and just to the left, we'll see here is our curve f of x. This black shaded region, all of that represents the area under the curve. So that whole black shaded region is the value that comes out of doing this operation. It will be that area. That area might be 10. It might be 400 billion. It might be 1.2. But it's a number. It's a number, okay? However, we do use a function, which is called the antiderivative, to evaluate that number, just like we use a function called the derivative to evaluate the slope of a line tangent to the curve, for instance, okay? So they're the same thing. The only thing you got to know about for right now is just what this symbol means, what we just went over, what it means in terms of an area under a curve. And you also got to know how to calculate the area under the curve. Notice the area under the curve represents the area that's bounded between the curve and the x-axis. If that area is like this area here and this area here that occurs above the x-axis, we call that area positive. If the area instead occurs below the x-axis, we call that area negative, okay? So just starting with the basics right now, but it's important you understand this before we go into our next topics, okay? Now something to kind of just put this in front of you right now, what I have on the next slide. This is not something that we are going to pay a lot of attention to in this unit, but it's going to be a huge point of emphasis on your overall understanding of what the purpose of integrals is, and it's this. Now, again, if it's a little confusing to you, don't worry. We will go over this many, many, many more times in subsequent units, but I want to just give it to you here so you can kind of see, well, what's the point of calculating an area under a curve? What does it give you? And that goes more to this whole idea of net change. And that's that the area under a rate of change curve. This is huge that I said rate of change curve, okay? It has to be worded this way or it does not work. You need the area under the rate of change curve, which we will call f prime of x, will give the net change in f of x. The absolute biggest mistake first-year calculus students make is they do not get the wording of this correct. They say the area under f of x gives change in f of x. That is not true. This, what was just said right there, the area under f of x gives change in x, was this. If I said the integral from a to b of f of x dx equals f of b minus f of a. That is not true. That will never be true, okay? This is what is true. The area under the rate of change curve. Notice that in here I have f prime of x, not f of x. That gives the net change in f of x, okay? Very, very, very important to understand that difference and the wording of this, okay? And we're going to come back again to this wording. In our first unit, we're really going to be focusing on the concept of area, but then in the next units, we're going to come back to this concept of how we get an integral to evaluate a net change. But for now, all you got to do is just know this. We'll go into this in more detail in future videos. But in the next videos, we're going to learn some methods for how we actually calculate these areas under the curve.